Now, for those who were not able to join the node voltage method, or I made a mistake, so for setting up, some of you they couldn't join the lesson. So I am taking a video of this node voltage method and a YouTube video. I'm going to give you the link so you can follow this up. Now, let me explain in general what is this node voltage method is. So this is the alternative to the any equations, any unknowns case. So classical method, classical. So it is something like that. So A has got j omega in it. So complex linear algebraic equations is the mathematical model. What we are saying is this: can we reduce this number of equations? Because if you've got 50 elements, you're going to write a matrix in the range of 100 to 100. So the size is very big and not easy to solve. So can we reduce the size of A? A should be square matrix. So when you reduce the size, that means you're going to reduce the number of equations and the number of unknowns. So this NE comes from NE minus ND plus 1 KVL equations for meshes and ND minus 1 KCL equations for nodes and NE definition relations. Now what node voltage method is related with this? It is based on these equations. If I write this number of equations, it's going to be less than 2NE, because when you add those three, you get this. So it is just one part of it. So it is based on that. When you if you reduce the number of equations through to ND minus 1, that's the reduction, isn't it? And that means you're going to write less equations. Less equation means you've got to have less number of unknowns. Less unknowns. How we are going to find this? So we are saying we are going to introduce a new unknown which is called node voltage. So we are going to define what node voltage is. On the other hand, the node voltage defined for the nodes as well, only for the nodes. So only for the nodes means ND nodes we've got, reference node voltage is 0. So if you if you take this away, reference node, what is left? ND minus 1. So if I define a node voltage for each node, this is going to be my new unknowns. The number of equations ND minus 1 and new unknowns ND minus 1. The square matrix is going to be, let's say, this type of matrix. The size of it is going to be ND minus 1 times ND minus 1 instead of 2NE times 2NE. X, so this unknowns in the X now, I'll make it different X. ND minus 1 of X is equal to B. So let's define the net voltage now. What is net voltage? A new page. And the node voltage is the voltage defined between a node and the reference. So if you are saying that what is the node voltage of node A, is the voltage that you measure between these 2 points. So it is going to be plus and minus. So you're going to connect the voltmeter red terminal to A and the black terminal to this reference. The voltage that you measure is the node voltage. We call it VA. Node A voltage. And VB similarly is going to be this. This is going to be this node voltage. If there is an element connected to these nodes, let's say this element A, what is element A voltage? I'll explain, I'll show it to you and then explain where we're going to use it. So if you consider this three terminals here, this make a loop, isn't it? So if you consider this loop and write Kirchhoff voltage law equation for this loop, what you're going to get is this element voltage VA, and this node voltage, since direction is this passive sign convention, same direction, it's going to be plus VB, so node voltage VB, that is. And if you come to its passive sign convention, the current is going to be this way. So these two currents are opposite to each other, so minus VA equal to 0. If I write VA, element voltage, so use the same color, VA is equal V small a, V small b. So these are node voltages, and this is element voltage. So the rule you can take out of this is this: any element voltage can be written in terms of node voltages. How it is written? It is easy. You're going to look at this element, current reference, beginning of your current reference connected node voltage minus these arrows towards node voltage gives you this element voltage. So this conclusion tells me I can replace any element voltage with node voltages. On the other hand, in our node voltage method and net, we are going to find the net voltages when we solve these equations. I'm talking about these equations now. This equation has got node voltages in it. When I solve the node voltages, I found only the node voltages. In the analysis, I need all the elements current and voltages. That helps me. Once you know the node voltages, you can find the element voltages. If you find the element voltages, then you can reuse the definition relation, find the element currents. So it tells me this node voltage, I can go to element, I can transfer the element voltages to node voltages, and the opposite, node voltages to element voltages. Now see what is the relation between node voltages and element voltages. In some cases, one element voltage could be a node voltage. In some cases, could be the difference. For example, if you consider this, so let's say this is reference. So if you consider this element A, node voltage for this node is, let's say this is 1 and this is 2 and this is 3. So for this node voltage is the voltage between those two. So VA is equal VD1 net volt. Why is that? Because this is VD1 is this node and the ground voltage, and this element is connected to that as well. So VA equal VD1. You might consider this minus V reference. V reference voltage is 0, then it is VD1. But if you consider that VD2 is not an element voltage. It is the voltage between these 2 points. You see, in some cases, node voltage could be an element voltage, but you cannot say this always. In some cases, it could be more than one element voltage. You've got to keep in this in your mind as well. Now let's come to the reality now. take this example and apply the method to this example. Now copy this, okay, and get it new page. Now in here, so I've got 3 nodes. I didn't consider this node because we know that in frequency domain, if 2 elements are connected in serial, capacitor and a resistor, you can replace it with one impedance. This impedance, so that means this element, equivalent of this element I can consider, then it's this element impedance is going to be 50 minus 100J. So I don't have to write a node voltage for this node, because if I replace these two with just this element, we've got only 3 nodes. Okay, for the first element, for the first node, so we said we are going to start with Kirchhoff current law equations, ND-1 equations. So first one, what is the equation? According to passive sign conventions, this independent voltage source current is downwards, so IS coming out of the node plus I is equal to 0. And for this one, minus I10, 10 ohm resistor current, plus I20, 20 ohm resistor current, and plus IL, inductor current, equal to 0. And the third one, minus IL, because inductor current comes towards this node, minus. For this one, plus, this is what is this? This is, I'll write it here. This is, since the voltage reference is given, this is current controlled voltage source. Current controlled voltage source voltage is 5I. So this element current is going to be written here. So it's going to be I current control voltage source current. In the definition relation, I can't see this. And then it is plus, because according to passive sign convention, current is downwards. And the last one is plus IE. Because of this impedance, I call this IE. So this reference is IE. Equal to 0. So 3 elements connected, so 3 terms. Now, as we said before, what we are going to do, now we are going to transfer all these to element voltages. So can I transfer this inductor independent voltage source currents to voltage? The definition relation of this element is Vs is 10, isn't it? So the current is not seen in this definition relation, so I can't use this definition relation. If you can't use definition relation, leave it as it is. For this I10, that is, by using the definition relation, I transferred this element current to element voltage. How is that? V10 over 10 is this element current, isn't it? Now I can replace now V10 with the node voltages. This is VD1 minus VD2 equal to 0. And the second equation, same as this, is minus V10 over 10 VD. So let me write now VD1 and VD2, okay? Because I already wrote it here, VD1 minus VD2 over 10. And plus I20. I20, this element current in terms of node voltages, this I can write this V20, voltage of it, over 20. V20 is equal VD2, because this is reference, isn't it? So VD2 plus IL voltage, this is VL over this impedance, isn't it? 10G. So what is VL? VL is VD2 minus VD2, VD3, VD2 minus VD3 equal to 0. The last one, IL the same as this, minus sign, VD2 minus VD3 over 10J. And now I came to this. What is the definition relation of this element? I wrote here, I repeated here. Current control voltage source voltage is equal 5E. In this definition relation, I don't see this current. So I cannot replace this current with this element voltage. So in this case, I'm going to leave it as it is. And plus IE, which is this element current, in terms of this node voltage over this impedance gives you that current, isn't it? VD3 over 50 minus 100J is equal to 0. Now look at these equations now. In these equations, I've got VD1, VD2, VD3 unknowns. I don't know IS, and I don't know ICCVS. Now these two unknowns left inside these equations. So my unknowns are 5 now, but my equations is just 3. So I need 2 more equations. How I am going to write this equation is the question. These are going to take us to the supplementary equations, how to write the supplementary equations. Now you don't have to memorize anything. What you remember is this. For these elements, we couldn't use the definition relations as we did it for the others. Now for these elements, I will be using these element definition relations that I couldn't use before in order to find the supplementary equations, additional equations, because I got 5, I need 5 equations because I've got only 3. So I'm going to write 2 additional equations which are called supplementary equations, and I'm going to write this equation by using the definition relations that I couldn't use before. What is it? This is independent voltage source. Definition relation is this. So I'm going to use this definition relation to find a supplementary equation. This is definition relation, not the supplementary equation. From that, I can easily say that this is a voltage of an element. It could be written in terms of node voltages. So what is this? Vs is equal Vd1. So Vd1 equal to 10. So this is supplementary equation now, supplementary 1. The other was this, that's the definition relation. I'll write this once again. Current control voltage source voltage is equal 5I. Now this is the definition relation that I couldn't use before. I will be transferring these node voltages. How I'm going to do it? This is an element voltage, as we said before, can be written in terms of node voltages. Look at this circuit. This element voltage is equal to VD3 because the other terminal is connected to reference. So VD3 is equal 5 times I. I is this current. This current is a resistor current. Resistor current is VD1 minus VD2 over 10, isn't it? Now this is second supplementary equation. Okay. Now I have got 5 equations, 5 unknowns. You might consider that this is not easy to solve, isn't it? There are many equations, many unknowns. But you've got to wait a minute. So we can reduce it to 1 equation, 1 unknown. How we could do that? By examining these equations. Look at this new unknowns that we introduce. This one and this one. For those, I couldn't use the definition relations. So this unknown seen only in one equation. So what does this mean? In order to find this unknown, I'm going to use this, leave this later on, leave it. And this one seen in this equation, leave it for a moment. What does this mean? Leave it later. Mean this. I am going to calculate VD1, VD2, VD3 first. Once I found all this, from this equation, VD1, VD2 already been found, I can find IS later on. Similarly, if I find that VD1, VD2, VD3, I can calculate this. So after VD1, VD2, VD3 calculation. So I leave those later on. So what is left, make it green, is this one. Okay. And this one. And this one. So VD1 equal to 10, that means that is the solution, isn't it? So you can replace all VD1s with 10s. 10. VD1, 10. So what happens? You've got 3 green equations. If you replace VD1s with 10, you've got 2 equations. So if you replace VD3 with VD2, so that means VD1 is already known. If you replace that VD3 with this one, this already known, so it's going to be VD2 included here only, isn't it? If VD2 only included here, you can find VD2. Once you find the VD2, use this, you can find the VD3. VD1 you already found, so you know VD1, VD2, VD3. Then you can calculate this IS. You can also calculate this because by using this equation. So this is called elimination method. Elimination method. When we use this elimination method, if we are doing by hand, if the number of equations are small. So if you got many number of equations, many number of unknowns, so you cannot use this elimination method. It takes quite a long time. So why we are teaching all that to you is to learn the mathematical model of a physical system. If you've got the mathematical model, then you can use the other tools in order to find the solutions. You can use MATLAB, you can use Python, do the mathematics, or you can use Proteus. Proteus writes these equations behind, but the solution, Proteus doesn't use this elimination method. It uses numerical methods, the course that you are taking in this semester. So by these numerical methods, they solve it. Why we are teaching it? Know this model and know what is behind Proteus in order to do the job. So that's the difference between the engineer and the technician at the same time. So at the end, what we found here, the node voltages. But analysis of a circuit, find out all the elements current and voltages. So what you're going to do, if you know the node voltages, you can write the element voltages. I explained here, didn't I? Here you are. If you know the node voltage, then you can write the element voltages. So you can find all the element voltages by using this rule. If you know all the element voltages, then you can use the definition relation, find these elements currents. So you can find this element currents for those definition relation which includes element current and voltage in the same definition relation. For those not being used, that means these are these unknowns. You see, this current, you already found that. So that means the voltages of these elements can be found in terms of node voltages. You already calculate. You found the element currents already. So for those, you don't need to calculate the currents. For the others, apart from those, you can use the definition relation of these elements to find these element currents. So you find all the elements current and voltages. So that is the whole method is about. So come back to this now. Here you are. This is all done. So at the end, all the elements current voltages, when I said all the elements current and voltages, we found the phasors of those. So from these phasors, you're going to transfer these phasors to time domain sinusoidal functions. How you're going to do it, I explained it already. Where is that? I'll show it. My computer stuck then. Anyway, it'll come back. Okay. So in which method I'll explain to you. So if in the source transformation here and this example, it's not the same circuit, but the steps are the same. You see here an element current phasor in terms of source phasor. So you're going to have a Cartesian complex number here. So at the end of your calculation, the equations that we wrote, you're going to end up with a solution like that. So in that solution, you got a Cartesian complex number. If there is a complex number in the denominator, so you're going to move this up. How you're going to do it? Multiply it with this. This has already been explained here. If you do both of the sides with the complex conjugate of this number, complex number, the underneath you're going to have a real number, so you transfer it to this complex number. You can transfer this complex number to a polar form from Cartesian to polar form. If you transfer the polar form, then it's going to be a polar form. Vs is already in a polar form. Because why it is in polar form? Because this is independent source. It is a sinusoidal function. As soon as you see the sinusoidal function, you can write the polar form phasor of it quite easily. So here you are. 10 is the independent voltage source amplitude. 30 is the angle. So you can. This is in the polar form. You calculated y in polar form. Do the multiplication operation. You get this. Now this is polar form phasor. Once you found that, how you can transfer the time domain? Very easy, isn't it? You're going to write 0.73. That is exactly here. And you write cos omega t is this part coming from the independent voltage source. And 89 degree comes from this y. Here you are. This 89 degree plus your source signal angle, so 180. This is how I just show you step by step how to do it. You're going to repeat, of course, all this for the node voltage method. Not this one. General techniques, node voltage method. Here you are. If you find all the VD1, VD2, VD3, then you're going to find all the elements phasors, and then from these phasors you're going to come to the time domain functions. Now remind you once more that these solutions are the particular solutions. That means steady sinusoidal solutions. The transient solution, homogeneous solution disappeared, isn't it? You cannot find this solution in frequency domain. So how you're going to check your conclusion? Use the Proteus, isn't it? You can check what the solution that you found here, sinusoidal functions, are the same in the Proteus. If they are the same, that means your collection your calculation is correct. So that is the end of this node voltage method explanation for those who missed to come to class. Okay.